Hello, this is Mustafa Abdurrahim. I will be presenting this paper, Novel Flexible Buffering Architecture for 3D Network on Chips. First, I would like to thank all my co-authors, which are listed in this slide here. So let's go to the outline of this presentation. First, I will highlight the congestion problem, the problem that we are dealing with in this paper, and how the flexibility solution proposed before can enhance or reduce this problem. Then I will highlight the inefficiency of the current solution, the current router that takes flexibility as a direction to reduce the congestion, which is called round robin flexible router. Then I will highlight our contributions, which are mainly three routers. All are flexible routers, but with different criteria. The first one is called minimum first flexible router. The second one, in another version from it, is called minimum first flexible router with YZ ports. And the last one is called inverse priority flexible router. Then I will show you the simulation results and how we architect these routers in hardware and the evaluation of the hardware. So let's highlight the congestion problem itself. So when you have the congestion problem is simple when you have, but with severe impacts. When you have an incoming packet requesting a busy buffer like this, in the conventional buffering router CBR, this packet will be blocked. Also, the flexibility solution is to redirect this packet to any free slot in any buffer in the router like this. So for example, here you can take this packet and move it to any one of these buffers to reduce, of course, the congestion and the blocking. Okay, and this solution is already proposed in reference one, and these authors came up with a router called round robin flexible router, or we call it so. Okay, and this round robin flexible router implements the flexibility, but with restrictions to avoid deadlock. So what they did there in this paper is that they analyzed the terms of the XY turn model, and they found that each one of these turns implicitly apply some rule in the network. So if these rules is as follows. The north buffer cannot store packets going to east, west, or north, but can store packets going to south or local. Okay, otherwise you have a deadlock. In the opposite is the west buffer. The west buffer, for example, can store packets going to east, north, south, or local, but only cannot store packets going to west. Okay, so if you follow these restrictions and apply the flexibility, you will get higher performance and avoid deadlock. So let's see an example. Again, here is our packet. The packet is again requesting the west port, but the west port buffer is full. Then the round robin flexible router, which is proposed in one, will check the next hop direction. For example, here it's north. Then it will store it in a buffer that can accept packets going to north. And here, in that case, it should be the east buffer or the south buffer, but it can't do that in the north buffer because north buffer cannot store packets going to north. Now, the idea is that how to choose the east or west, which one of these buffers I should choose. And the criteria they implemented there is actually round robin. That's why they call it round robin. So round robin flexible buffering is that you apply round robin so that, based on the round robin, you should choose one of them. So for example, if you used the south buffer before, then you will choose the east buffer in that case, and so on. Okay, and actually this will lead us the inefficiencies of the round robin flexible router, which one of them is the round robin criteria. So let's see here the same example again. Okay, and assume that the round robin will choose east buffer, so this packet will be stored as a tail in the east buffer. Also, if the south buffer were chosen and the south buffer can store packets going to north, the packet will be ahead, so this will have less queuing time. Otherwise, this scenario here with higher queuing time because the packet is tail. Another inefficiency came from the fact that the flexibility is only active when you have a full buffer, requested to a full buffer. So you have there the hardware. The hardware is implemented for the flexibility, but you are only using it when there is a request to a full buffer. And this is also a source of inefficiency. So again, the same example, but now the west buffer has a free slot. and again the packet is going to north. So all these three buffers, west and east buffer and south buffer, can store this packet. So since the flexibility is not active, the packet will be stored as a tail in the west buffer. So it should have a higher queuing time. Also, if it was stored in the south buffer, it will be ahead of the queue and it would have less queuing time. And this will lead us to our first contribution, which is minimum first flexible buffering router, which deals with these specific two problems in the round robin flexible router. So the first problem is that the round robin criteria, and here is the example in which the packet is stored as a tail, and here is our new criteria, which is it choose the packet, or I'm sorry, choose the buffer with the minimum occupancy. So in here, south buffer is the minimum occupied buffer. It has no packets at all. So the packet, so the router would choose south buffer over the east buffer to store this incoming packet. So it's ahead now. And the second inefficiency, in which the flexibility is active only when there is a request to a full buffer. Now our minimum first flexible router will activate the flexibility all the time, so that in that case here, even if we have a free slot in the west buffer, the minimum first will choose south buffer again to store the incoming packet. Okay, the minimum occupied one, so that in both cases you have the packet in a in a advanced place in the queue, so it will have less queuing time. We also extended the restriction table that I showed you maybe 4 slides earlier, so that the flexibility can work in a 3D environment. So the original round robin flexible router was implemented or designed for 2D network on chips. So the authors of the previous reference only checks the ternets of XY, but in a 3D environment you have 3 planes. You have the XY plane, the original XY plane, and you have XZ plane and YZ plane. So we make analogy between the XY turn model and XZ turn model and YZ turn model. So we have now 24 turn. We analyzed all of them and used a new table here, okay, so that the 3D flexible routers can follow in order to operate correctly without a deadlock in a 3D environment. So let's see an example. The east buffer now can store packets going to west, north, south, up, down, or local, but only cannot store packets going to east. The opposite was one of the Z buffers, up or down. For example, the up buffer here can store packets going to down or local only. Otherwise, it can't store any other packets going to some other direction. Otherwise, you will have a deadlock. Now the question is how, if you have many minimum occupied buffers, okay, how to choose any of them. So for example here, we have here 2 packets. Packet 1 is heading west, packet 2 is heading down, okay, as the next top direction. And as you see here, all the buffers are completely free. Okay, so now we have the question, which one to choose? So you have many minimum occupied buffer, so which one to choose? Okay, so we have here an observation. Packet 1 is heading west, and the only buffer that can store packets heading to west is actually the east buffer. Okay, and this is actually a property for packets flowing in this direction. Okay, only east or west buffer can store these packets. Also, packets heading in the direction, for example here packet 2 that is heading down, can be stored in east, west, north, south, and up buffer. Okay, so if the choice is arbitrary, this may be inefficient. So let's see an example. So packet 2, if we assume that packet 2 will be served first before packet 1, and we arbitrarily choose the east buffer, then when it comes to serve packet 1, we'll find that the only buffer that can store this packet is already blocked, or or become full by packet 2. So one is served, the other is not. But we came up with a criteria called ZYX buffering based on this observation, in which we check buffers in that order: Z buffers, which are the up and down buffers, then Y buffers, which are the north and south buffer, then the X buffers, which are the east and west buffer. And we make the east and west buffers at the end because we know these buffers can the only buffers that can serve packets flowing in the X direction. So if we apply this, packet 2 is going to down. So we will check first the up and down buffers. Down buffers are going to store packets going to down. So we have the up buffer, and the up buffer is free. So packet 2 will be stored in the up buffer. Now, when it comes to packet 1, when we check the buffers, they can't store packets going to east, west. North buffer again cannot store packets going to west, but because of the deadlock. But east buffer now can store packets going to west. So both of them is served. This will lead us to our next router, which is called minimum first flexible router, YZ. So the idea is that you have a hardware, extra hardware, the hardware overhead. Of course, the minimum first criteria requires some overhead, area overhead. So the idea how to reduce such overhead and at the same time have flexibility and good performance. And we refer that to some observation near the ZYX buffering criteria. So there is observation that packets flowing in X, is get less benefit from the flexibility. So let's see an example. Here is this packet going to east, and only the west buffer can serve packets going to east. So the flexibility will not be, will not be beneficial here. Okay, so you have a hardware with no value. But then packets going in the Y direction, for example, south, can be stored in 3 out of 6 buffers, and much better with packets going in the Z direction, for example, up, can be stored in 5 out of 6 buffers. Okay, so the idea is that you can remove the flexibility hardware from the export, east and west port, and only keep the flexibility hardware in the north and south and the up and down ports, ZY ports only. So this will reduce the hardware overhead, at the same time give you better performance because of the flexibility. And we call this a version of this version is minimum first flexible router, YZ. The third contribution is called inverse priority flexible router. Again, the criteria here is again to reduce the hardware and at the same time get flexibility and more performance. So we found that we can get higher performance without checking for the minimum first or whatever by using very simple criteria, which is a first fixed order search. So in that case, whenever you receive a packet in the router, you search all the time in that order: up buffer, down buffer, north, south, east, and west. Okay, or something similar to ZYX: Z buffers, then Y buffers, then the X buffers. Okay, and the order between the Z buffers, down before up or up before down, doesn't matter. Okay, what matters is that Z buffers, then Y buffers, then X buffers. But now the difference, the reason is different. It's different from ZYX, although it's similar. If we look at the restriction table, we find that the X buffers are the most flexible. They can store many packets with many, directions. But the least flexible ones are the Z buffers. Okay. And we found that if we make the search order as opposite of that, from the least flexible to the most flexible, this will make a balance in the buffering balance. Okay. At the same time, this will give you higher performance. So let's see an example. So to stress on the order, let's assume the order is opposite. Okay. So let's assume we have another router, a hypothetical router called forward priority flexible router, in which the search order is from the most flexible to the least flexible: east, west, north, south, and up and down. Okay, and we have another an example, a simple example in 2D. So the search order should be for the forward buffer should be north, south, up, down. I'm sorry, north, east, west, north, south, and for the inverse priority it will be north, south, east, west. So let's see. Let's see what's a forward priority flexible router. What will happen? It's a flexible router, but the search order is different or forward or opposite to the inverse priority. So we have the search order as east, west, north, south. So in that example, we have 3 packets, packet 1, packet 2, packet 3. All of them are heading to R1. Okay. The next top direction of packet 1 when it reaches R1 is west. The next top direction of packet 2 when it reaches R1 is north. Packet 3, next top direction when it reaches R1 is south. So let's start by packet 1. Packet 1 when it reaches R1, the next hop is west. Okay. So we're gonna go in that order. So we'll check the east buffer first. All of them are, as you see, are free. So the east buffer is free, and the can store packets going to west. So packet 1 will be stored in the east buffer. Then we're gonna serve packet 2. Packet 2 is heading to north. We start in the same search again, east, and east has a free slot, so packet 2 will be stored again in packet 1. Then packet 3 with the next top direction of south. Again, we start the search from east, and east still has one free slot now. So packet 3 will be stored as a tail in that buffer. So all of them is stored. Yes, that's good, but they are stored in the same buffer. Okay, so they will be dependent on each other. So if packet 1 is blocked, then it will block all the other packets. Now let's see what's happened with the inverse priority. So with the inverse priority, when we do from the least flexible to the most flexible, this will guarantee some level of fairness. So let's see, packet 2, it's going packet 1 first. It's going to as a next hop west, and north cannot store packets going to west. South, same problem. East can, so packet 1 will be stored in east. Then packet 2 is heading to north. So if we start by north cannot store packets going to north, but south can, so packet 2 stores in the south buffer. Then packet 3 is going south, but north can store packets going to south. So you have here, we have implicit fairness, buffering fairness, or buffering or balancing. In buffering is a balance, in buffering is the packets, so that all of them, if you know the surrounding as also has free slots, can move forward and be stored in their next hop directions. Now let's see some simulation results. I'll just show you some sample of them. So for example, for the uniform traffic, this is the average delay, and as we see here, inverse priority, which is very simple, as we say, just fixed order of search. Okay, got almost same performance as the minimum first flexible router, and of course, minimum first is really powerful one. It's a superior one. Minimum first YZ. Okay, although we reduce the hardware, we still outperform the conventional buffering router, and at the same time, we got almost same performance as a round robin, the older router that we are comparing against. But as we see later, it has lower area overhead than the round robin router. We also look at another metric, which is the blocking count. So we count the number of blockings in the network. So if you whenever you have a packet that cannot be stored anywhere in the router, you count this as a blocking. So as you see here, again, the conventional buffering router has a maximum number of blocking, then a minimum first YZ and the round robin, and lastly inverse priority and minimum first flexible router. Another metric here, which is also interesting one, which is the packet order. So we also count how many times we have a packet stored as a head, and how many packets were stored, for example, as a tail. So for example, if you have here a buffer of depth of 4, so you have the first brace, which is the head, second, third, and fourth, which is a tail. Okay, and as you see here, the criteria of minimum first really works, and is the highest number of increase in the head packets goes to the minimum first routers, and also the highest number of reduction in tail packets also goes to the minimum first routers. The second one that I will show you here is devolved video benchmark traffic. Okay, so it's a real traffic, and here is it's a communication task graph between the tasks. Okay, and here is another contribution of this paper. So we know that packets flowing in Y or Z has less get benefit from the flexibility than packets moving over X. In the conventional buffering router, all are the same. You have almost one hop each time. But we know for flexible routers, they can store packets moving in Y or Z with more flexibility than packets moving in X. So we added or modified the objective function, which is reducing the delay by reducing the number of hops, minimizing the number of hops. We added some restrictions. Okay, so we did the minimization such that hops in Z is greater than or equal to hops in Y, and hops in Y is greater than or equal to the hops in X. So we increase, so for the same number of hops, we increase hops in Y than X and Z than Y, because in Z we even more flexible than Y. Okay, and this is really very beneficial and give us very good performance even for the round robin flexible router. So even if you want to use the old round robin flexible router, use such kind of criteria, you will get more benefit out of it. So as we see here, we increased the saturation injection rate by 45%, which is really amazing. The last item here we have in the outlines in the hardware architecture and evaluation. So this is basically the normal or conventional buffering architecture. It's a very normal router. And here is our highlighted in gray, our main modifications, we can say. The main modification lies in the flexibility controller module in here, which is the one that represents the flexibility module. So this module receives the packets, it checks the direction, and applies the criteria, whatever it's minimum first or inverse priority or whatever you wanna do, and distributes these packets to the buffers. So this is the internal architecture of the flexibility controller. You have here for each port a buffer allocator. This buffer allocator receives the request and the buffer information, the occupancy, for example, for the minimum first. Then based on the criteria, it will initiate request to one of the buffers. And for each buffer, we have a simple arbiter, fixed priority arbiter, that receives this request and handles them according to some prioritization technique. So in here, for example, this is the internal structure of the buffer allocator. So this buffer for the minimum first, for example, you have here a sorting network. It's a very famous sorting. It's called odd even sorter network. It's very optimized one, which receives the buffer occupancy and sort them in that way. Also, we have a routing logic module, which receives the destination address of the incoming packet, process it and knows the required output port. And based on this information, the request handler will initiate request. Of course, for a round robin flexible router or the inverse priority flexible router, the odd even sorter is not required. We only need this. We only need the routing logic and just the buffer occupancy information to know to which buffer I should initiate the request. Here is the synthesis report. So the highest overhead goes to the minimum first, of course, because of the sorting network. But again, this guy gave us a very good performance in all of the traffic patterns we see. Minimum first YZ has the lowest or the minimum hardware resources. And also inverse priority and round robin show very similar area overhead. It's still inverse priority flexible route, as we saw earlier, has more performance than round robin, for example, in the uniform traffic. So this is a conclusion and summary of our contributions. So we introduce a new flexible routers and and that outperform the old round robin flexible router and also conventional buffering router. We introduced three of them with three different criteria or design choices. We also extend their deadlock freedom criteria to 3D environment. We also modified the task to core mapping to get more benefit out of flexibility for real benchmark traffic. And we also introduce a novel hardware optimization techniques such as the sorting network to reduce the hardware cost for this architecture. So thank you very much. And if you have any question, just email me to my email that I showed you in the first slide. And thank you very much for your time.